So in today's video, we're going to start out with chapter 7. So we're going to start with 7.1 and 7.2. 7.1 is super short, and it's just going to give you a couple of definitions of different types of random variable. And then we are going to go more in depth with one of those types in 7.2. So types of random variable, there are two of them. There are discrete random variables and there are continuous random variables. Question is, what is the difference? I'll start out with a discrete random variable. So a discrete random variable, okay, it's just something that has a countable number of outcomes, okay? Let's say rolling a dice, okay? When you roll dice, the possible options are 1, 2, 3, 4, 5, and 6. There are a countable number of outcomes. When you toss a coin, there are 2 outcomes, heads or tails. When you draw a card out of a deck of cards, there are 52 possible outcomes as there are 52 cards in a deck, okay? Each one of these has a set number of outcomes and you can count that number of outcomes. So a discrete random variable is a random variable which has a countable number of possible outcomes. Okay. So whenever you describe a discrete random variable, and this is actually the random variable we're going to be talking about today, whenever you describe a discrete random variable, you are going to create a table which has your probability distribution. And that table is going to tell you the possible outcomes. So it's going to list the possible outcomes on the top row and the probabilities of each of those possible outcomes on the bottom row. Okay, so for example, if we're rolling a dice, its probability distribution on the top row, I would put my possible outcomes. Okay, so on the top row, my possible outcomes, I'm going to call them X, are 1, 2, 3, 4, 5, and 6. On the bottom row, I'm going to put the probabilities of each of those things occurring. So we actually denote that by the probability that X is equal to a certain outcome, we'll call it little x. Okay, so it's the probability for the first one, it would be the probability that X is equal to 1. What is the probability that I roll a 1? Well, that's 1 over 6. What's the probability that I roll a 2? Again, 1 over 6. Okay, in the case of rolling a die, it's actually the exact same probability for each one. Okay. Not the case with every single thing that you're going to do. Okay, you're going to come across tables, probability distributions, where each outcome has a different probability, and we'll see some of those later on. But in this case, it just turns out you actually have something called a uniform distribution that we'll look at in 7.3, where every single thing has the same probability of happening. But the main thing to take away from this, and the reason it's a discrete random variable, is because you have a countable number of outcomes. You have a finite number of outcomes, and you can tell the probability of each one of those outcomes. You put them into a table, and that table is called a probability distribution. The other type of random variable you're going to have to know about is a continuous random variable, and we're going to get to that one in chapter 8. But a continuous random variable is a random variable that can take on any value along the real line. So for example, let's go with time, okay? Something can take exactly an hour, okay? But something that you say takes an hour could have in fact taken 1 hour, 1 minute, 1 second, and 3 milliseconds, okay? You can really narrow it down, and you can get decimal values, fractional values of even a millisecond. So even though normally we'd say, well, those two things happen at the same time, they could be milliseconds apart. Okay, so you can have these things that take on this really, 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 really precise value, and it can be any value along the real line, not just 1, 2, 3, 4, 5, 6 that we saw before. They can take on decimal values between those values. That is a continuous random variable. So a continuous random variable is a random variable that can assume any value on a continuous segment of the real line. Okay, so you may say, well, something takes anywhere between 0 and 10 minutes, but it could take 8 minutes, 4 seconds, and 2.77 milliseconds, okay? So it can take any value on that real line. Okay. So classic examples of continuous random variables. Time is one of them. Height is another one. Weight, okay? Something can weigh 100 pounds, or it can weigh like some tiny some tiny thing of an ounce, let's say, okay? So it can be like 2.67543 ounces, okay? So you could take on this really, really, really small decimal value of even an ounce. Okay, so it can take on any value along that real line. Now, we're going to move on to 7.2. And 7.2 discusses kind of the overview of discrete random variables and some stuff that you need to know about them. So we've talked about probability distributions, okay? So a discrete probability distribution, as we've seen before, I'm just going to outline this again. A discrete probability distribution consists of the discrete random variable values along with their associated probabilities. Okay, so as I said, on the top row, you're going to have all possible values of that discrete random variable. So when rolling the die, we had the outcomes were anywhere between 1 and 6. Okay, so we had 1, 2, 3, 4, 5, 6. They were our discrete random variable outcomes. They were the only possible outcomes. On the second row, we had the associated probabilities. We had the probabilities of each one of those outcomes happening. Okay, two things to always look out for when you do this. Number one, make sure that those probabilities actually add up to 1. Okay, so in the case, let's go back here, when we looked at rolling a die, okay, if you added up each of these probabilities, okay, you get 6 over 6, which was 1. So make sure whenever you do a discrete probability distribution that the probabilities actually add up to 1. The second thing to look out for that they may try and catch you out by doing this is by putting down a probability that is either less than 0 or greater than 1. Okay, we know probabilities from chapter 6, they have to be somewhere between 0 and 1. Probability of 0 means it's never going to happen. Probability of 1 means it's definitely going to happen. It's always going to happen. So make sure that the probabilities, each one of those probabilities, must be between 0 and 1, and their sum must equal 1. It can't be less than 1, it can't be greater than 1. Okay, so each one individually is between 0 and 1, and they must add up to 1. We're going to look at a few different types of discrete random variable. In 7.3 and 7.4, we're actually going to look at the uniform distribution and the binomial distribution. Both of those are discrete. So we're going to look at different types of these, but I'm just giving you a general overview of this for now. Here's an example of a probability distribution that you may come across. So this time we're looking at a coin. So we actually did this when we were looking at coins back in chapter 6. And we were looking at tossing a coin 3 times. Okay. When we tossed that coin 3 times, there were 8 possible outcomes. Okay. You could have 3 tails. You could have heads, tails, 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 heads, tails, 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 heads, and etc. So there were 8 possible outcomes when you tossed a coin 3 times, okay? There were 8 possible different combinations of what we could get. We know that the probability of when we flip this coin, the probability of getting heads is 0.5, okay? The probability of getting tails is also 0.5. So the question is, what is the probability distribution for the number of heads observed in 3 tosses of a coin? Okay, so we're looking at how many possible heads could we get when we toss a coin 3 times. Okay, well, if we toss a coin 3 times, the maximum number of heads that we can get is 3. Okay, we could get heads every single time we did this. Okay, toss a coin 3 times, we get 3 heads. Okay, so we know that 3 heads is a possibility. Okay, we also know that if I toss a coin 3 times, we may get 3 tails. We actually may never get heads whatsoever. So we may also get 0 heads. In between that, we can just get 1 head and 2 tails, or 2 heads and 1 tail. So I may get 1 head, or I may get 2 heads. So from 3 tosses of a coin, I can get 0, 1, 2, or 3 heads. Okay. Now, the question is, what is the probability of each of those happening? And then I can create this probability distribution. Okay, they've actually done this in columns rather than rows. But what they've done in this first column here is they've put all possible outcomes of the number of heads. Okay, they're looking specifically at the probability distribution for the number of heads observed. So your possible outcomes are 0 heads, 1 head, 2 heads, 3 heads. Now the question is, what is the probability of each of those outcomes happening? And they put that in the second column as opposed to the second row like I did earlier. Okay, but the probability of each of those happening. Now, we've said before, the probability of getting 3 heads. Okay, there's only 1 out of our 8 possible outcomes that has 3 heads. Okay, you can only get 3 heads 1 time out of the 8. Okay, there are 8 possible outcomes. 3 heads was only 1 of those 8 possibilities. So the probability of getting 3 heads was 1 over 8. Same way, probability of getting no heads, well, the only way that you get no heads is by getting tails, tails, tails. So the probability of getting no heads is also 1 out of 8. Okay. Then if we go back, you can go back to the chapter 6 video when we dealt with this, and we looked at the other outcomes, okay, like heads, tails, 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 heads, tails, etc. Okay. There were 3 outcomes out of the 8 that gave us 1 head and 2 tails. And there were 3 other outcomes that gave us 2 heads and 1 tail. So there is a 3 in 8 chance that I'll get 1 head, and there is also a 3 in 8 chance that I'll get 2 heads. That completes this probability distribution table. They've actually put the events as their final column in case you wanted to see which ones they were, but the actual probability distribution table itself is just between here and here. Okay, it's the possible outcomes, possible number of heads, which is what we're looking at, and the probability of each of those happening. Okay. They may ask you, for example, what's the probability of getting at most 1 head? Okay, so the probability of getting at most 1 head is the probability that your random variable x is less than or equal to 1. Okay, that's how they would write it. The probability of getting at most 1 head means that you're looking at the probability of your random variable x being at most 1. So it's going to be less than or equal to 1. Okay, well, the only outcomes that are less than or equal to 1 are 0 and 1. So it would be the probability that x was equal to 0, the probability that you got no heads, plus the probability that x was equal to 1, the probability that you got one head, which was 1 over 8, plus 3 over 8, which is 4 over 8, which is 1/2. Okay. So whenever they give you kind of like a combined situation where they want the probability that a random variable is less than or equal to something, greater than or equal to something, greater than or less than something, okay, just go ahead and add up the probabilities that the random variable is equal to those values. Another type of situation that you can get is actually where they give you the frequency distribution. So we're going back a few sections here when we looked at frequency tables. They can give you a frequency distribution where they give you the possible outcomes and then they give you the frequency of each of those outcomes. That is not a probability distribution because they've only given you the frequencies and not the probabilities of each of the outcomes. Now, in this case, this particular table, it was looking at the number of computers sold in a computer store, okay? So the number of sales each day. So there were no sales on 40 out of the 200 possible days. If you actually add up the frequencies, it adds up to 200. So this guy sold no computers on 40 out of the 200 days. He sold one computer on 20 out of the 200 days, two computers on 60 out of the 200 days, etc. Okay, so they've given you the number of sales that he had and the frequency of that number of sales, okay, over these 200 days. So if you are ever given a frequency distribution, you can create a probability distribution out of that, okay? All you have to do is basically exactly what I have just said, okay? I just told you that this guy had no sales of his computers on 40 out of the 200 days. Okay, so he had no sales on 40 out of the 200 days, which was 0.2 of the days. So on 20% of the days, which is 0.2, on 20% of the days, he had no sales. Okay, he had one sale, so he sold one computer on 20 out of the 200 days, okay, which was 0.1. So on 10% of the days, he sold one computer. So all you have to do, if you are given a frequency distribution and you have to create a probability distribution, just divide each of the frequencies by the total and it will give you the probability of that particular outcome happening. And you should find when you do that, that those probabilities again add up to 1. So if you added up 0.2, 0.1, 0.3, etc. all the way down, you would get 1. Okay, so make sure just as a double check at the end that those add up to 1. If they don't, then you know you've gone wrong somewhere. Again, you can do, let's say we wanted the probability that he sold at least 3 computers on any particular day. What is the probability that he sells at least 3 computers? Well, the probability that he sells at least 3 is the probability that he sells 3 or the probability that he sells 4, okay? So the probability that he sells 3 is 0.2, probability that he sells 4 is also 0.2, which gives us 0.4, okay? So he has a 40% chance of selling at least 3 computers. As a heads up with probabilities when you deal with this discrete random variable, okay, this thing here, in discrete random variables, and only in discrete, this does not work for continuous. In discrete random variables, I could have also written the probability that x is greater than or equal to 3, also as the probability that x is strictly greater than 2. Why? Well, the probability that x is greater than 2 in a discrete random variable, we are looking at all numbers that are strictly greater than 2, so we're not including 2 here. Well, in a discrete random variable, we don't have to worry about the decimals that are between the values of 2 and 3. So in discrete random variables, the only values that are greater than 2 are 3 and 4. So the probability that x is greater or equal to 3 are also the same as the probability that x is greater than 2. Okay, so either way, in discrete random variables, you can write some of these as different things. So I could have also said, let's say I wanted the probability that x is less than or equal to 2. Okay, well, x is less than or equal to 2. The values that are less than, or the outcomes that are less than or equal to 2 are 0, 1, and 2. Okay, so in that case, I could have also written the probability that x is less than, strictly less than 3. Okay, if they're less than or equal to 2, I'm including 0, 1, and 2. If I'm looking at x being strictly less than 3, I'm not including 3. My next value that is less than 3 is 2. So when I'm looking at x being less than 3, I'm also looking at 0, 1, and 2. Okay, so just as a heads up, sometimes you can write these outcomes when you're looking at an inequality. You can write these in a couple of different ways. So just be aware of that. If they ever give that to you, make sure that you know the difference between less than and strictly less than, or sorry, less than or equal to, or strictly less than, or greater than or equal to, or strictly greater than, because you can write some of these in different ways. We don't really deal with these a huge amount. These come up a lot more when we look at continuous random variables, but sometimes what they'll do is they'll write a discrete random variable and its probability in terms of a function rather than a table. You can turn the function into a table. It's not too difficult to do as long as you don't have a ton of values. But what they may say is, well, our outcomes here are 1, 2, 3, and 4. Okay, there are possible outcomes. The probability of each of those outcomes happening is given by this particular function, x squared over 30. So what you're going to do, okay, you can create a quick table here. You can have your outcomes x, so let's say 1, 2, 3, and 4, and then your probabilities of each of those outcomes happening. Well, the probability that x is equal to 1, I just plug in x is equal to 1 into my function. So I've got 1 squared, which is 1, divided by 30. So the probability of 1 happening is 1 over 30. Probability of 2 happening is 2 squared over 30, which is 4 over 30. And then 3 happening would be 9 over 30. You can simplify these fractions if you wanted to. Okay, so you actually figure out the probabilities based on what the function is and what the outcome was. So you just plug that value of the outcome into the function and it will give you the probability. And then you can turn that into a probability distribution into this table. You see that the probability that anything else outside 1, 2, 3, and 4, the probability of any other value happening is 0. It's like saying the probability of rolling a 7 on a die. Well, it's 0 because there's only 6 sides to a die. So we know that the only possible outcomes here are 1, 2, 3, and 4. We can figure out their probabilities and we know that any other values are going to have a 0 probability. Okay. Also, as a double check, just to make sure that you haven't missed something somewhere or that you've actually calculated this correctly, whenever you have a probability distribution function, make sure to actually add up the probabilities at the end to make sure that they actually add to 1, because otherwise you may have plugged something in incorrectly, like you may have plugged 3 in incorrectly into your function and it gives you a random probability that isn't correct. So just to make sure that each of your values, each of your probabilities are between 0 and 1 and that they do all sum to 1 at the end. And in this case, they do. Okay. Now, this is where we're going to start dealing with like a really important thing when we deal with discrete random variables. And that is something called the expected value. Just as a heads up, for everything else that I'm going to talk about here, it can be done on a calculator. So whenever you do this from now on, unless it's something super, super simple, make sure that you actually pull your calculator out to do this. I'm going to show you how to do it by like pen and paper, just so you know what your calculator is actually doing. but please use your calculators for the rest of this. You actually know how to do this, but I will run through it again at the end. So an expected value, it basically tells you kind of like what it says. It's the expected value, the expected outcome that you would basically expect to get. Okay, so it's the outcome that you would expect to happen almost most often. Okay, it's an average of all of your outcomes with their probabilities, and it tells you which outcome you expect to get most often. Okay, which one is most likely, basically. Okay, it's a weighted average. Okay, so keep that in mind, because that's what we're going to be doing on our calculators, which we've already done back in chapter 4 when we looked at weighted averages. But all it is just a weighted average where the variable is weighted by its probability, and it will tell you the most likely outcome. Okay, now that outcome may be a decimal value, just as a heads up. It may be a decimal. Don't worry about that. It is just an average. It's like whenever you average stuff out normally, okay, it's normally not equal to one of the outcomes that you have. Like when you average out your test scores, your average normally isn't equal to one of the test scores. It's normally in between a couple of the test scores. So your expected value, okay, even though it's like the expected outcome, it may not equal one of the outcomes, but it will give you a rough idea if you averaged out your outcomes, what you would expect to get on average if you completed this thing multiple times. Okay, it is just a weighted average. So let's write that down. It is a weighted average where each variable is weighted by its probability. Okay. So the expected value of a discrete random variable x is, our expected value is denoted by e of x, where x is in square brackets. Okay, so e of x, you sometimes get it in parentheses as well. Okay, just as a heads up, it can be done in different ways. All it is, we actually sometimes even denote it as mu, the mean, okay, because all it is a weighted average. It's a weighted mean. Okay, it's going to look slightly weird, but bear with me, because it's not going to look much like an average. Okay, we take each outcome and multiply it by its probability. Okay, so let's come back to one that we've done before. Okay, if I wanted the expected value of this, okay, I would take each of my outcomes x and I will multiply by its associated probability. So I would do 1 times 1 over 30, 2 times 4 over 30, 3 times 9 over 30, and 4 times 16 over 30. Then I would add all of those results together. Okay, so we're going to sum them together at the end. This doesn't look much like an average, okay? You're adding some stuff together, but you're not dividing by anything, okay? Normally an average is where you add all of the possibilities together and divide by the number of them that there are. Our weighted average was where we took each of our possibilities, multiplied it by its frequency, and then divided it by the total number of things that there were, okay? You are doing the same thing here. Think back to our frequency distribution example, okay? If I took each of my outcomes and multiplied it by its probability, so let's come down to here. If I did 2 multiplied by 60 over 200, okay? I'm multiplying my outcome by its probability. When I do that, if I do 2 multiplied by 60 over 200, I'm doing 2 multiplied by 60 and dividing by 200. So I am taking each of my outcomes, multiplying it by its frequency and dividing it by the total number of things that there are. So by just multiplying by the probability, I am multiplying it by a frequency and dividing it by the total number. So all I have to do, a simplified version of that, is this. I just take each outcome, multiply it by its probability, and then I add all of those results together. It's exactly the same as a weighted average. Okay. So here's our example here, okay? Again, I'm looking at the number of computer sales. So if we went back to our previous example, we saw that the guy had between 0 and 4 sales in any one day, okay? And the probabilities of each of those happening were 0.2, 0.1, 0.3, 0.2, and 0.2, okay? I then multiply each of my outcomes by its probability. So here I've done 0 times 0.2, here I've done 1 times 0.1, then I've done 2 times 0.3, 3 times 0.2, 4 times 0.2, okay? Then I add all of those together, and that's what we've done down here. I've added all of those results together to give me my expected value of 2.1, okay? So my expected number of computer sales in general is about 2.1 computers a day. If I averaged out how many I sold, or how many this guy sold on any particular day, it averages out to about 2.1 computers a day over the 200 days. That is what the expected value does. It's a great comparison tool so that you can see, okay, well, my particular company sells on average this many computers a day over 200 days. Let's look at what another company did. I can look at their average amount of sales, computer sales per day, okay? It's a great way of comparing two different companies, two different things, okay? So it's just the expected number, in this case, of computers that I would expect to sell on any one day is around 2.1 on average. So the next thing that you'll need to know is the variance and then the standard deviation, the square root of the variance of that discrete random variable. So let's start with the variance of a discrete random variable. Okay. Again, I'm going to give you the formula that is used for this, but please use a calculator. I'm going to show you how to do it on a calculator in a second. So the variance, we denote that by sigma squared, exactly as we've done before. You can also sometimes see it denoted as V of X. And all we're going to do, let me write this down and then I'll explain what your calculator does. I take each of my outcomes X, I subtract the expected value, okay, that weighted mean. I subtract the expected value from each of my outcomes. So coming back to here, I would take each of my outcomes 0, 1, 2, 3, and 4, and I would subtract 2.1 from each of those values, okay? I then square that number for each of my outcomes. So I do outcome minus expected value squared. I then multiply that number by the probability of that particular outcome happening. So come back to here, I would do, let's say, 0 minus 2.1. I would square that outcome, so negative 2.1 squared. I would square the outcome and then multiply it by the probability of 0.2. Okay, I'm going to do the same with the next one. I'm going to do 1 minus the expected value of 2.1. I would square my outcome, so I would square negative 1.1. And then I would multiply it by the probability 0.1. And you're going to do that with every single one of your outcomes. And then you're going to add each one of those together. You're going to add them all together for each one of your outcomes. That is the variance of the discrete random variable. Again, because your probability is basically the frequency of that thing happening divided by the total number of things that happened, okay? By multiplying by the probability, you are doing multiplying by the frequency and doing like a weighted variance and dividing by the total number of things. So this thing is just kind of like a simplified version of a weighted variance. Okay. The standard deviation of a discrete random variable, as always, is just the square root of the variance. So the standard deviation of a discrete random variable okay, we denote it just by, as it's the square root of sigma squared, it's just sigma. So it is just, is the square root of the variance. Okay. I'm going to run through the previous problem. So I'm going to run through this problem and find the standard deviation and the variance. So on a calculator, remember when you find a weighted mean, okay, by finding the weighted mean, it will give you the standard deviation, okay? You can then, as the standard deviation is the square root of the variance, I can square my standard deviation that is given on a calculator to find the variance for this particular problem. Okay, so I'm going to run through that on a calculator. As I said, please use a calculator as much as you possibly can. Try not to go through all of this work by hand. It's just too much going on, okay, and it's much easier to make a mistake that way. So I would highly, highly recommend you use a calculator, and I will just remind you how to do weighted averages and stuff on a calculator for this particular problem. Okay, so we're now going to look at how to do this on the calculator to find both the expected value and to find the standard deviation for this data set. Now bear in mind here, we can also find our variance, and we just do that by squaring the standard deviation. Okay, so let's say, okay, let's go back to the problem that we were looking at. In list 1, I put my outcomes. So these are the numbers 0, 1, 2, 3, and 4. These were the numbers of computers that this guy sold in any one day. It was anywhere between 0 and 4. And then we figured out previously the probabilities of each of those things happening. So I've put my list of outcomes in list 1, and I've put my list of associated probabilities in list 2. Okay. Now what I'm going to do is go to stat, calc, one variable stat. Okay, my list is my list of outcomes, so that was list 1. My frequency list, remember we are weighting the outcomes by their probabilities. That is how we are doing this weighted average to find that expected value. So for my frequency list, I want list 2, so second and 2 for list 2, and calculate. If you have the TI-83 or you have one of the other models of an 84, you will have to do one variable stat, list 1, comma, list 2, and it will do the exact same thing as we've done here. That top value there, 2.1, that was our expected value, okay? That was the expected number of computers that this guy was going to sell on any one day. Then if we scroll down here, too far there. Okay, here we have sigma x, which is 1.37 roughly. This is our standard deviation, okay? Remember, we are weighting our standard deviation by using those probabilities. So that is our standard deviation. If you need the variance for this discrete random variable, all you are going to do is square this number here. So this is your standard deviation. If I take the square of that, I'm going to get my variance. So you are computing this in the exact same way as we did for a weighted average. It's just that now your weights are the probabilities instead of the frequencies, and we can still get our expected value, that weighted average, and we can get our standard deviation and our variance for this discrete random variable in this case. I'm actually going to go through one more example actually by hand that comes up on your homework. There's some extra work that you need to do in order to complete this problem. It's not as simple as just seeing this probability distribution table and then just figuring out the expected value and stuff on your calculator. There is a bit more work to it, and it's actually using some stuff from chapter 6. So this particular example that I'm going to do is that you're drawing 2 cards without replacement from a standard deck of cards. Okay. You're playing a game here. So if both the diamonds, so if you get 2 diamonds, okay, if both cards are diamonds, you get $30. Okay. Otherwise, you pay $4. Okay. So if you have this standard deck of cards, you draw 1 card out, it's a diamond, and then you draw a second card out and it's also a diamond, you get $30. However, if you draw anything else, so you may draw 1 diamond, but you may then draw a club. In that case, you owe $4. Okay, so if you draw anything other than exactly 2 diamonds, you owe the other person $4. And the question is, what is the expected value of the game? How much are you expected to win or lose on average? If you played this game multiple times, what will be the average that you will win or lose on any particular game? Okay, so whenever you get one of these, I would make a probability distribution table. Okay. Okay. Your 2 possible outcomes are either you gain $30, so it's a positive $30, or you're going to lose $4. Because you are losing $4, I'm going to write that as negative $4. Okay, so you're either gaining $30 or you're losing $4. The question is, what's the probability of each of those things happening? Well, let's go back to our standard deck of cards. We are drawing 2 cards without replacement. In order to win $30, I need 1 diamond and then another diamond. You see the word and, you think of the intersection. So I want the probability of getting 1 diamond and then another diamond. Okay. From 6.3, we know how to calculate this. It's the probability of getting a diamond, so the probability of getting our first diamond, multiplied by the probability of getting our second diamond, bearing in mind we've already drawn a diamond. So the probability of getting a diamond and a diamond is just the probability of drawing that first diamond multiplied by the probability of drawing another diamond, given that we've just drawn a diamond. Okay? Well, the probability of drawing a diamond in the first place. Okay? There are 13 diamonds out of 52 in a deck of cards. So we've got 13 out of 52. Now, we've already pulled 1 diamond out of that deck of cards and we're not replacing it. We're doing this without replacement. So I've taken 1 out of the 13 diamonds away from the deck. I've also, by doing that, taken 1 card out of the 52 away from the deck. So my probability of now drawing a second diamond, given that I've already drawn 1 diamond, is the 12 diamonds that remain out of the 51 cards that remain, which comes out to 0.05882. Okay, so that's the probability of me getting $30 in any one game. Okay, you've got about a 5 or 6% chance of winning $30 in any particular game. What's the probability that I lose $4? Okay, Well, if I get anything other than exactly 2 diamonds, so I could get a diamond and a club, I could get a club and a spade, I could get a heart and a spade, I could get a heart and then 1 diamond, okay? Any of those combinations leaves me with losing $4, okay? So anything other than 2 diamonds means I lose $4, which means the probability of losing $4 is 1 minus the probability that I win the $30, okay? It's 1 minus the probability that I get exactly what I want. So it's 1 minus 0.05882, which comes out to 0.94118, okay? So I have each of my outcomes and I now have the probabilities of each of the outcomes. That is the part that's like the difficult part of this problem and why I wanted to run through it, because it's not as intuitive as you might think when you first see the problem. So I have each of my outcomes and I have their probabilities. Now I go back to what I know about expected value. If I want the expected value of a particular problem, I just multiply each of the outcomes by its probability and then I add those results together. So I'm going to do 30 multiplied by 0.05882 plus -4 times 0.94118. So my expected value of my gain is 30 times 0.05882 plus -4 times 0.94118. That comes out to -2. So I expect, on average, to lose $2 a game. So if I played this game, let's say 100 times with someone, and I averaged out my winnings and how much I lost, it would come out to an average of losing $2 a game over those 100 games. That's what I would expect to see happen. Okay. Hopefully that helps as you go through your homework. If you have any issues with this, please let me know and I will see you in the next video.